Hi. Hey, I just wanted to say thanks to everybody for being here this morning or this evening, wherever you might be, and I really appreciate you coming. I hope the information is useful to you, so let's go ahead and get right into it. I'm on our first slide here, and I'm just going to review what we're going to cover very briefly. We're going to look at some basic TL07X information, some of the housekeeping things for the op-amps. We're going to look at gains, inverting gains, not inverting gains, input-output coupling with AC and DC as far as AC versus DC and just what that means. We're going to look at a precision full-wave rectifier circuit, which is really cool, and you'll use a lot in your analog synthesizer work. We'll check out a Fuzz Tone just so you can kind of get an idea how that works, and you could take that away and you could build that this afternoon if you wanted to on a breadboard. We're going to talk about comparators and how a comparator works. We're going to add hysteresis to it, look at pulse width modulation, something that you can do with some of the waveforms from your synthesizer. We're going to look at a window comparator. We're going to look at some uses for capacitors and how they can help us in little areas with our op-amps. A brief look at an integrator and just how that works. We'll look at battery power. Brief look at some filters and then some online filter calculators you should know about. So let's get right into inverting gain here and just a few things, or excuse me, the basic TL07X information. I'm sorry. All right, the TL07X is a good op-amp, the TL07-1, the TL07-2, and the TL07-4. And we can see here that we have the single op-amp package, the TL07-1 CP, and these are all plastic 8-pin dip packages. They also come in ceramic, and they also come in the SOIC packages, the small outline IC packages. But I pretty much always use the dip packages myself. So we see the TL07-1 with one op-amp, TL07D2 with two, and the TL07-4 when you need four op-amps. Now in the TL07-1, we notice that there are null offset pins. This is something you don't have in the TL07-2 and the TL07-4, but we're going to look at how we would adjust offset in those op-amps as well. Now, you're going to want to read the entire data sheet for full details, for sure. But the maximum you want to apply to these op-amps is plus and minus 18 volts. The minimum is plus and minus 3 volts. The maximum input, they're saying plus and minus 15 volts, but that's when you have plus and minus 18 volts powering your op-amp. You don't want to go above the supply rails on the inputs of your op-amp, or you're going to run into problems, I can guarantee you that. So always keep your input within the power supply voltage, let's just put it that way, within several volts, as you can see. The unity gain bandwidth for the op-amp is 3 megahertz. That's a nice unity gain bandwidth, and this is a very useful op-amp in many scenarios. The current draw per amp is about 2 milliamps. So you want to keep that in mind whenever you're designing. If you're looking for low current design, you want to use as few op-amps as you can in your design. The inputs are P-channel JFETs, and they're very high input impedance, 10 to the 12th ohm. That's extremely high. And so these things are good for sample and holds. They're good for filters and so forth. No current. When you're designing with these op-amps, you want to consider that really no current is flowing into the inputs. And we'll look further as we get into circuitry. The output voltage swing with supply is going to vary. So if you're powering from batteries at plus and minus 9 volts, your output swing, you don't want it to go beyond about plus and minus 7 volts, or you're going to start to get clipping and distortion. At plus and minus 12, you can see that's about plus and minus 10. At plus and minus 15 volt power supply, it's about plus and minus 13.5 volts as far as what the output can do without distortion. Now the other thing, you don't want to overload the outputs of the op-amps and expect to get good results. You want to keep your output load resistance above 2K for your best audio results. So keep that in mind. When you're driving something with your op-amp, if there are more than one thing that is drawing current from the output of that op-amp, you want to make sure that all of those sources together are at least above 2K for best audio results. Also, when you're using these op amps, always bypass the package with a 0.1 microfarad ceramic cap close to the power pins. Now, you could also use a 1 microfarad tantalum cap or even a 10 microfarad tantalum cap as well, because they have such low equivalent series resistance. All right, so that's basic information. Let's move on. Now we're going to look at inverting gain briefly. All righty, okay. Now there's a few things I want to explain from this slide. First off, I'm showing the op amps with power supply connections and bypass capacitors shown and so forth. Typically, you're not going to see these things on a schematic. The bypass capacitors might be somewhere, they're located somewhere else on the schematic and just be off to the side. And the reason is your schematic can get really crowded if you're trying to put power supply connections to every op amp and bypass capacitors on every op amp power supply pins and so forth. So to simplify, usually you won't see that. Okay, just wanted to make that point. All right, our gain formula, very simply, -1 times the value of the feedback resistor, that's the RFB, divided by the value of the input resistor, that's the RIN. All right, so basically you can get a ton of gain out of an op amp. If you've got a really small signal and you want to gain it up, you can get gains as high as 100 or 1,000 just by following this formula. Now the thing is, the offset voltage, the input offset voltage of the op amp will also be amplified by the gain factor. So you can see with the TL07X op amp down to the lower left there are two additional pins. These are these null offset pins I talked to you about before. And what we have is we've got a 100K resistor just across those two pins, and then the wiper going off to the minus voltage you're powering the op amp with. In this case, it's -12 volts. And what you do by adjusting that trimmer, that's a trimmer resistor, is you set the output to 0 volts. And what you're doing actually is you're adjusting the input offset voltage, and that input offset voltage, of course, propagates through the whole op amp and appears at the output amplified, and so you've got to null that out, and you can get your output right to 0 very easily with this TL07X and these offset null pins. So now, though, what do you do if you don't have offset null pins, as in the case of the TL07IV and the TL07II? Well, let's go ahead to our next slide. We're going to look at that. Alrighty, so now, offset adjust or biasing an inverting op amp. And a great book that if you can find it somewhere, it's very old. It's this National Semiconductor Linear Applications Handbook, Linear Brief 9, Universal Balancing Techniques by Robert Dobkin. It's a great book, this Linear Applications Handbook. I would just advise you to go out there, find it, and buy it. All right, well, now let's take a look at the op amp on the left here. All right, what's happening is, of course, we've got gain being applied. If we've got a feedback resistor and an input resistor, we have gain being applied. Now, one thing I didn't mention back on the previous page was that gains don't always have to be, 1 or 2 or 100 or 1,000. They can be fractional. So if I put a larger resistor for my input resistor and a smaller resistor, so let's say I put 10K for my input resistor, this RIN, and 100K for my feedback resistor, I will have a gain of, let me start that again. If my R input resistor is 100K and my feedback resistor is 10K, I'll have a gain of 1/10. Okay, so keep that in mind. You can get fractional gains in the inverting configuration. So our gain formula is pretty much the same. It's going to be your feedback resistor divided by your input resistor. However, notice what we're applying to the non-inverting input. We've got a trim pot here, this 100K trim pot. One end's at +12 volts, the other end is at -12 volts. And we're applying that via the pot's wiper to this little resistor divider, RDiv1 and RDiv2. Now, if all we want is a few millivolts of adjustment on the output, we're going to make RDiv1 very high in relation to RDiv2. We might make RDiv1 like 1 meg and RDiv2 1K. And if we have gain in the system, the op-amps, feedback resistor, and input resistor are providing gain for that input. Remember, they're also going to give gain to the offset voltage. So if you've got a lot of gain, but you only want a few millivolts of offset, well, then you may want to make RDiv1 1 meg and RDiv2 100 ohms. You see what I mean? And the reason is because the offset you're applying to the non-inverting input is going to be amplified by the op-amp's gain factor. So keep that in mind. And now in this first scenario on the left, we're putting the offset into the non-inverting input. Okay? On the right, we're applying it to the inverting input. Now let's go back to the left for a second, because not only can you adjust the op-amp's output by a few millivolts, as I've explained, depending on the ratio here of RDiv1 and RDiv2, you could adjust the op-amp's output by volts. So there might be a time when you've got one of your synthesizers that's operating, let's say a triangle wave, and it's plus and minus 5 volts, but it oscillates about minus 5 volts for some strange reason. You want to bring that up. Well, what you can do is you can apply that to an op-amp with a gain of 1, and then by making RDiv1 about, let's say if we said 100K and RDiv2 100K, now we're really applying quite a bit of voltage here to this non-inverting input. We're going to be adjusting the output up and down by volts instead of millivolts. So keep that in mind. And when you need to adjust a signal, when you need to level shift a signal, this is one of the ways you can do it. And now if you needed the output of this op-amp to be in the same phase as the input signal, you could simply put the output into another inverting op-amp with a gain of 1. In other words, your feedback resistor and your input resistor would have the same value. Let's, for conversation's sake, feedback resistor 100K, input resistor 100K. You've just got an inverter here, and it's with a gain of 1. All right, well, let's look at the scenario on the right, and this is where we're applying the bias to the to the inverting input. Notice we've got our non-inverting input just grounded. We have gain being applied because we've got the feedback resistor from the output to the inverting input. We've got our input resistor there. And that gain formula is pretty much the same. It's just going to be your feedback divided by your input resistor. But now we've got this, also we've got the bias resistor coming to the inverting input from the wiper of the trim pot used to adjust the output offset. Now once again, if you only want a few millivolts of offset adjustment, you want to make our bias very high. And again, it's also dependent on your feedback resistor. Let's look at a scenario where the input resistor is 10K and the feedback resistor is 100K. Now we've got a gain of 10 from this TL07X op-amp here, but we only want to have the output go a few millivolts. Well, we may have to make our bias as high as 2 or 3 megohms, maybe even 10 megohms, in order to get that little bit of adjustment on the output, since we're already applying gain of 10 with the amplifier, you see. And if you have higher gain, again, you may have to make our bias even lower, or break our bias into like kind of a 3 resistor divider, where coming right off of the wiper, you'd have a resistor going to another resistor to ground, and then a third resistor basically taking the place of our bias and going into the inverting input. Then you could really attenuate what was coming off of this trimmer with that little network. And regardless of the fact that even if you have high gain in your system, in your amplifier, you can still reduce that offset adjustment to just a few millivolts. All right, but if you want more, again, reducing our bias in relation to our feedback is going to allow this pot to give you a lot of adjustment of DC offset on the output of your amplifier. There are times when you might, instead of making this R adjust, this 100K, a trim pot, that might be mounted on your panel as an offset adjustment for the particular circuit. All right, so this is how you offset adjust the inverting op amp. Well, let's move on. All right, non-inverting gain. Whenever you use inverting gain, you are taking your input signal and you're shifting it by 180 degrees. You're flipping it over. When you don't want to do that, you can go with either non-inverting gain, as we show here, or, as I said before, follow the output of your inverting op amp with another inverter with a gain of 1. And then, of course, you'll once again be in phase with the input signal. But let's look at our non-inverting gain. So up here at the top left of the page, we see our first example. Now we have our non-inverting input as the input for the op amp. This could be coming from some high impedance sensor. It could be coming from a piezo. It could be coming from a capacitor used in a sample and hold. And you're going to get the highest impedance condition with no resistor from that non-inverting input to ground. Your gain is a little different from the inverting gain formula. First of all, it's not inverted, so you have no -1 in front of this. You have your feedback resistor divided by the resistor going to ground in this case. That's going to set your gain factor +1. So keep that in mind. With non-inverting gain, if you're not applying any type of division, a resistive division to your input, your signal is never going to be able to be amplified with less than a gain of 1. You're not going to get the fractional gain here with the non-inverting setup. Now let's move over to the right, and we see we've put a stabilizing resistor from the non-inverting input to ground, and that resistor is typically going to be a higher value, 100K or a 1 meg. And now the reason that's there, let's say that you have a capacitor that's taking an AC signal and connecting it over here to this input without the stabilizing resistor. Well, we all know op amps are not perfect circuit elements. The inputs have what is called offset current. You're going to get the slightest tiny little current that's flowing either into or out of these inputs. It's in the picoamp range. But if you have a capacitor sitting here with no stabilization resistor, that current coming out of the non-inverting input or going into the non-inverting input can charge or discharge that capacitor. Your output of your op amp will start to ramp up or ramp down. Occasionally you'll find that it's not working at all, and you'll look at the output and here it's at saturation voltage and you're wondering what's going on. It's because you don't have a stabilization resistor from that non-inverting input to ground, and that capacitor that's coupling the input to this input is charging up or discharging below ground. So keep that in mind. If you have a circuit you've built and you do have non-inverting inputs that are only connected to a capacitor and you have unusual behavior, look at that. Now, last example on non-inverting gain is the unity gain follower. That's down in the lower right. What we've done here is we just take the output of the op amp and we connect it to the inverting input directly. Now, whatever we're putting onto the non-inverting input is going to be immediately reflected at the output, and it will be fed back to the inverting input and satisfy the op amp to keep those two inputs at the same voltage, which in this configuration where you have negative feedback, that's essentially what you're doing. Again, some examples on the gain, just so we'll go over one of these. If your R ground resistor is 10K, your feedback resistor is 100K, put it into the formula, you're going to get a gain of 11. Okay? Now we go to this scenario, the last one, which is the ground resistor is 100K, the feedback resistor is 2K. Now you've got a gain of 1.02. You see, back in the inverting, if we were in inverting configuration, our input coming in through this R ground instead of R ground going to ground, we would have a gain of 0.02. But remember, in the non-inverting gain, it's hard to go below 1, and it's impossible, essentially, when you have this configuration in the non-inverting gain. All right, now, we notice again, if we have that TL07 op-amp, we would be able to use the input offset null in order to offset our output. Well, what do we do here when we want non-inverting gain, but we still want to offset the output? Well, let's look at our next slide. Okay, here is how you offset, adjust, or bias a non-inverting op-amp. And let's talk about this for a while. Okay, we've got our feedback resistor, our RFB. We've got our RGND, our ground resistor. And notice our ground is going to ground, but through this 100 ohm resistor, R2. All right, and now our input is being fed to the non-inverting input. We can either stabilize that non-inverting input with a resistor to ground if we need to, or we don't need to if the input is coming from a low impedance source like the output of another op-amp. Okay, so keep that in mind. Now let's go back up to our bias network. We again have our trimmer pot, 100K. We're at plus 12 volts and minus 12 volts on the pot. Now, again, if we only want a few millivolts of output offset adjustment, make our bias very high. Okay? If we want the output to be a range over several volts, well, there's a couple of things we want to do. We might want to reduce R2, or excuse me, increase R2 from 100 to maybe 1K, or maybe even 10K, depending on what we make our bias and the gain of the system with our feedback, our ground, and R2, which also goes to ground. So we can have the output, again, ranging over several volts by adjusting this trimmer or a panel-mounted pot if we want that to be part of our module's functionality to have the output be able to be adjusted DC-wise over a large range. So again, keep this in mind. You'll use this a million times in your designs, and there you go. Let's move on. All right, now we're going to talk about input-output coupling, AC versus DC. You've probably gone over this before, but I'm just going to say it simply. If there is a capacitor in your way, you are AC coupled. Okay? If you don't have a resistive or DC path wherever you're going in your circuit, and there's a capacitor in the way, you're DC coupled. And DC is not going to go through a capacitor. So you are now AC only coupled. So let's look at the non-inverting configuration, AC coupled. What we see is we've got that capacitor going into the non-inverting input. We have our stabilization resistor, which I highly recommend you always use. You could make it like 1 meg, you could make it 100K. But bear in mind, the capacitor and resistor will form a high-pass pole. That's why I typically just make our stabilization 1 meg. Then that pole is so low, you don't really care about it. You're not cutting off any frequencies you're interested in. We're still getting our gain from our feedback resistor and our ground resistor. And that formula is still the same, R feedback divided by R ground plus 1. And we notice on our output, we have another capacitor. Again, to block any DC offset that might be present on the output of the op-amp from getting to the next stage of whatever circuitry we're feeding. Well, let's drop down to the non-inverting configuration DC coupled, and what do we see? Well, we're coming into this input. Depending on where the input is coming from, if it's a high impedance source, you want to keep our stabilization. If it's a low impedance source, you really don't need our stabilization. So again, bear in mind one less component. But also notice there are no capacitors in the paths of the input or the output, purely DC coupled. Okay? And that's basically the difference. Let's go ahead to the right of the page, to the top there. Look at the inverting configuration AC coupled. Again, we see capacitors in the path, and that always tells us, well, only AC is going to get through here. DC is not going to get through here. Now, once again, we're going to talk about the fact that the input capacitor and the Rin form a high-pass filter, again, even here in this inverting configuration. Well, why? Well, let's take a look. We notice we have our non-inverting input connected to ground. All right, and as I've said before, the whole job of the output of the op-amp is to keep the inverting input in this configuration at the same voltage as the non-inverting input. And thus, that non-inverting input is called a virtual ground in this kind of a configuration, because the output, if the input's coming in here and it's going positive, the output's going to go negative in order to pull some current out of here and keep this inverting input at ground. You see what I mean? So that's why that's called a virtual ground. Again, only AC signals coming in, only AC signals going out through our 10 microfarad bipolar capacitor. Oh, also bear in mind, these bipolar capacitors, they're made with electrolytic capacitor technology, but it's almost like having two electrolytic capacitors in the same can with their negative sides connected together and their positive poles coming out as the leads, which is a little trick you should know. If you don't have a bipolar capacitor handy in a value, take two electrolytic polarized capacitors of twice the value, put their negative poles together, and use the positive poles as the leads to your now 10 microfarad bipolar capacitor, okay, or 11 microfarad if you use 22 microfarad capacitors. All right, again, dropping down to the inverting configuration DC coupled, no capacitors in the path. It's really as simple as that. If you put a capacitor in the path of a signal, only the AC part of that signal is going to continue past that point, okay? And also keep in mind the high pass pole you get in the non-inverting configuration AC coupled between the input capacitor and the R stabilization. And remember, you also have a high pass pole with the input capacitor in the inverting configuration between the input capacitor and the value of the R input capacitor, which goes to that virtual ground. Alrighty, let us move on. All right, here we see an application where we have an AC mixer versus a DC mixer. Now, in the AC mixer, we have our inputs into these potentiometers. We're using them as voltage dividers, adjustable voltage dividers, and we're taking from the wiper of the potentiometer, we're going through a capacitor. We are AC coupled. So whatever we're putting into this input, only the AC portion is going to continue on through Rin and then be amplified by this first TL07X. Again, we're on the left side of the page, AC mixer. Now notice we've got our feedback resistor and our input resistors from all of these various inputs. Each of these inputs can be assigned a different gain if you want to, by just making the Rin the value you want for the gain you need depending on the feedback resistor. So let's say our feedback resistor here is 100K. Well, if Rin on the top input was 10K, well, that input would provide us with a gain of 10. If Rin on the second one down was 100K, that input would only provide us with a gain of 1. All right? And if you wanted to attenuate, say Rin would be 1 meg, then we'd have a gain of 1/10. Now, what we're doing with the output of that first mixer amp is we're going through 10K resistor into the inverting input of an amplifier that has a 10K resistor from the output to the inverting input, and it is an inverter with a gain of 1. So our signals will now be back in phase with the input on the output. All right, let's go over to the DC mixer. In the DC mixer, we're not using capacitors on the input or the output. We want to keep the DC in the signal. Let's say you're mixing the output of an ADSR and the output of a low-frequency oscillator on two of these inputs. Well, if it was AC coupled, it really would be kind of lame because you'd only get the attack portion, part of the attack portion of your ADSR if it was set to real high attack. But in this case, it's just going to follow whatever the DC voltage that's coming out of your ADSR is. It could be the slowest attack in the world, and this guy doesn't care. He's going to just let that DC go on through this system. We're going to mix the signals in the first amplifier. And once again, the feedback resistor and the input resistors will determine the gain for each of these inputs. You can have a different gain on each one if you want. Now, here's the thing to bear in mind with the DC mixer, is that when you're inputting, let's say, an ADSR in one channel, a low-frequency oscillator in one channel, and another low-frequency oscillator yet in another channel, and these guys are going, let's say, plus and minus 5 volts, and they're oscillating about ground. Well, if all three peaks give us some kind of a constructive interference where essentially they grow, you're going to have a 15-volt peak, and you may well clip depending on how you're powering your op amps. So in these DC mixers, you want to keep your gains low, maybe even a gain of 1, I would suggest. Once again, coming out of the output of the mixer amplifier, we go through a 10K resistor into a op amp with a 10K feedback resistor, gain of 1. All of our modulation signals are now back in phase with the inputs, and we're ready to go. So there's some applications showing AC coupling, and in the AC side, again back to the left side, you're going to be putting audio signals in here, guitar signals, microphone signals, synthesizer signals, those types of signals that you want to mix in an audio fashion. The DC mixer, control voltages. That's basically what you're going to mix there. Now, can you mix audio signals through the DC mixer? Absolutely. As long as they're oscillating about ground and they don't have a lot of DC offset in them, this would work fine. You could go ahead and mix them. They'll be fine. All right, so that's AC coupling, DC coupling, and an AC mixer and a DC mixer, just to show you how those things work. Let's move on. All right, now we're going to spend some time talking about the active precision full wave rectifier. This is the totally cool circuit. You'll use this all the time for envelope followers or when you want to make an instrument to gate signal, all types of things. These are in the vocoder. The MFOS vocoder uses a lot of precision full wave rectifiers. So let's get into how this works and how remarkable op amps are in this particular circuit. It's just really cool. All right, what the thing about rectifiers is when you use just diodes require about 600 millivolts before they even begin to conduct. You need to forward bias the diode in order to get it to conduct. So if you want to rectify a small amplitude signal, well, that's going to pretty much get in the way because you can't even get the diode to conduct until 600 millivolts. Well, what can we do to fix that? Well, let's see how this works. It's ingenious. I wish I knew who invented this, but I don't. I'll just tell you that. If someone does, if they want to put it out in the chat, that'd be great. But this circuit's been around a long time, but let's go through it now. All right, so we see our input signal over here to the left of the page. It's this sine wave, and it is starting to go low. It's starting off by going low. So what's happening? We're going to drop the voltage directly on R3 and feed it into the non-inverting input of the op amp. Now, the output of the op amp, notice two things are happening right now. D2 and D1 are not conducting. Neither of them are turned on because when we just are starting to go down from the baseline, we're basically at ground, and we're just coming down a few millivolts, let's say. So what happens here on the output is that it starts screaming to get to negative saturation. That's that red line. So the first red line is the op amp starting to go toward negative saturation. But it gets down to the point where D2 begins to conduct. And D2 starts to conduct, and we can see, as you move over a little bit, you see those little negative going dips that are by R4. That's what you see at the non-inverting input of U1A. Now, keep in mind that U1A, if we look at its feedback resistor, it's 10K. Its input resistor is 10K. So this is going to be giving us a gain of 1 in an inverting configuration. But when we're coming in through the non-inverting input with these negative going spikes, they are going to have a gain of 2 applied to them. All right, so if you follow the orange arrow, you go up, and you see what you would see if you were just putting in those negative peaks. They would be getting that gain of 2 applied to them, and that's basically what they'd look like. But, of course, they're mixed with the signal that's coming from the inverting input of U1. Now, what am I talking about? Remember what the job of the op-amp is to do. In this configuration, when we have inverting feedback, it is trying to keep the inverting input at the same voltage as the non-inverting input. And op-amps are amazing in that if you take a look at the signal that appears on the inverting input, you'll be surprised to see the same thing you see on the non-inverting input. So you're looking at the inverting input, so you're going to see the same AC signal as you're seeing that you're applying on the non-inverting input. Well, let's continue and see why. All right, so after this negative going peak comes back up, what's going to happen? Well, D2 is going to turn off. D1 isn't turned on yet because there's not enough voltage to turn it on. And so, again, the op-amp's going to say, hey, I've got to keep these inputs together. I better start going high. And so he starts shooting towards positive saturation. But what happens? D1 turns on, and we get feedback coming through to satisfy the inverting input and keep those two inputs at the same voltage. So now that AC signal, the same signal that we see on the non-inverting input, so let me clarify. The AC signal we see on the inverting input is now being fed over into the second op-amp, you see, through R1, but it's being inverted. So we see the inverted version of it there above those amplified peaks. But now what's happening? The op-amp is actually adding those two things together. So as the inverted negative going peak starts going high, what do we see? Well, we see a copy of that, only inverted and with a gain of 2 going low. What's going to happen? We're going to get destructive interference to the point that we actually turn the top waveform that's going up, we turn it upside down, because this times 2 gain on these negative going pulses takes this, does destructive interference, and now, wham, look at that. That on the output now, we're looking at a very faithful representation of the input waveform, only fully rectified now. All right, and the nice thing is, again, going back to U1B's output, those little shifts that are made, those red lines, which are when the op-amp is trying to go to either negative saturation or positive saturation, are the limiting factor in how faithfully this precision full wave rectifier rectifies. But due to the fact that the TL07 is a very fast amplifier, those things happen in a very, very short time, which is why, in essence, what this guy does is he takes the forward diode drops out of the picture and thus rectifies our input signal, even with very low amplitude, into a very nice looking rectified signal on the output. Now, if you want positive peaks instead of negative peaks, just turn both of those diodes around, okay? And you'll get positive peaks coming out instead of negative peaks. Now, of course, I've shown a sine wave being put into the input, but this could be a guitar signal, a keyboard signal, your synthesizer signal, whatever you want, and you will see a faithful rectification on the output. Now again, the levels of the signal you want to put in here, you want to observe the same type of restrictions you would anytime. Keep the levels below the power supply voltage, and again, to take a few volts off of that yet, because you don't want to be turning parasitic devices on with too much voltage coming into the inputs of your op amps. So again, this precision full wave rectifier is so cool, you'll use this a million times. Let's move on. All right, we're going to talk about a fuzz tone. And as I said, this is something that you could put on your workbench this afternoon and be playing your guitar through. Well, let's look at what's going on here. Well, we're feeding our input to the non-inverting input, okay? So the input's coming from the jack. It's being dropped across this 100K R1. We're going through this 0.033 microfarad, and that's really not a, in this particular instance, that's not a critical value. That could be 0.1, it could be, 0.05. We're dropping then on this 1 meg R2, and then that signal is being applied to the non-inverting input. Now, on the inverting feedback, we have a lot of gain. We've got a 1 meg resistor R4 between pin 6 and pin 2, the output and the inverting input. And we've got a 10K resistor going to ground. Now let me think here. I think that's going to give us like a gain of 100. All right, so we're really going to be gaining up our guitar signal that we're putting in here. So what's going on with these two diodes that are in the feedback network? Well, when the output goes above the forward voltage of D1, D1 is going to turn on, and he's going to clip the signal and keep the signal from going above the forward voltage of the diode. And he's going to feed back to the non-inverting input, and he's going to satisfy the op amp's desire to keep the the non-inverting and the inverting inputs together as far as voltage is concerned. It wants to keep them at the same voltage. Now, when the output goes low, it's going to eventually turn on D2. D2 then will limit the low excursions again to -6 volts. And what's essentially happening in a fuzz tone is you're clipping the guitar signal so that you get more of a square wave type sound from it. So give this a shot, put it on your breadboard, experiment with it. It's a very cool circuit. We put this 22 picofarad capacitor in the feedback network to quell oscillation. This is quite a lot of gain. When you're getting into gains of 100 and more, and even at times with less than that, you may want to add this compensating capacitor across the feedback resistor in order to quell oscillation. All right, let's move on. Well, now we're going to be talking about comparators. Let's take a brief look here. Now, what we see is we have a TL07X being used on the top, and this is an inverting comparator configuration. We are applying 6 volts to the non-inverting input, and that's called our threshold voltage, okay? Because we've got 12 volts here and two 100Ks, and we're just splitting that in half. We're putting 6 volts to pin 5 there, the non-inverting input. Now, on the input, we've got a triangle wave that's going from 0 volts, and it's going up above 6 volts. You can see there, it looks like it's probably going to like 8 or so if this was to scale, and then down and up and down. So what's going to happen? Well, when you see no feedback resistor from the output of your op amp back to your inverting input, that's a comparator. It's not going to be applying gain to a signal. It is simply going to be causing the output to be shifting from its positive saturation voltage to its negative saturation voltage, depending on what's on the input. So we see our input. It's ramping up from 0. It hits 6 volts, and we follow that blue line over there, and bam, our comparator shoots all the way to minus saturation, and it stays there until that triangle wave peaks, starts to come back down, goes under 6 volts, and bam, it shoots all the way high to positive saturation. That's what a comparator does. It simply compares the voltage on the inverting input to the voltage on the non-inverting input, And if the input to the inverting input is lower, well, then the output of your comparator will be high. If the input on the inverting input is higher than that on the non-inverting input, your output will be solid low at negative saturation. The non-inverting comparator we won't spend as much time on. It is simply we apply the threshold voltage to the inverting input instead of the non-inverting input. Here we're going to be applying our input to the non-inverting input of the op amp. And as we come up from 0 volts and we pass 6 volts, what's going to happen? Well, the non-inverting input voltage is going to get a little bit above 6 volts. Again, the operation of the op amp is going to say, hey, I've got to try to feedback and make that inverting input be the same as the non-inverting input. But since there's no feedback path, it can't, and so the output just shoots high to positive saturation, stays there until the voltage on the input goes below that threshold voltage of 6 volts, and then, bam, we shoot low. So these are your two comparators. Now, here's the thing to keep in mind. Whenever there is noise in your system, let's say the power supply has a little bit of noise on it. Doesn't have to be much. And we'll go back and we'll look at our inverting comparator here at the top. So let's say that the non-inverting input that is seeing the threshold voltage sees some noise on it. Well, now, as your input approaches, let's say you're looking at your input, it's ramping up here from 0. It almost gets to 6 volts, but the noise here on the non-inverting input, because of some noise coming through the power supply, let's say that it knocks this down a little bit. It goes to maybe 5.95 volts, and wham, your output is going to change state. Well, let's say that that noise goes up a little bit. Now your output's going to change state again. You see, you can get what's called chattering on the output. And if you're ever wondering, you know, you've got the output of a comparator connected to some logic, and you got a diode on the output, so you're only feeding out the positive voltage through the diode. You're dropping that onto a resistor that's going to ground, so that you just are getting the positive excursions. And well, I completely forgot what I was going to go into there. That was an important one too. Oh, here's what it is. You're talking about, you're going into logic circuitry with the output of a comparator. The chatter can be very fast. So in order to see it, you have to turn your scope sweep speed up a lot and look very close at the edge of the output of your comparator. Because where you think, oh, I should only be getting 1 transition, you might be getting 5. And so your logic is just not going to be doing anything you expect, because you're not getting clean pulses coming out of there. Well, how can we get clean pulses? Let's move on. We add hysteresis. All right, now let's talk about comparator hysteresis. What's happening here, hysteresis is essentially brought into play in your comparator by feeding positive feedback to the non-inverting input. All right, so now let's see what's happening here. We're applying 6 volts via our little voltage divider here to the non-inverting input. And now, though, we have put this 3 meg resistor from the output also to the non-inverting input. Well, with a comparator, you're always going to be sitting at either positive saturation or negative saturation. All right, in our case, we're going to say we're at positive saturation to start, okay? So the output is at, if this was powered by plus and minus 12 volts, your output is going to be sitting at about 10.5 volts, 10 volts. And current is going to be going through this 3 meg feedback resistor, the positive feedback resistor, and instead of getting 6 volts here at the non-inverting input, you're going to get something higher than 6 volts. See, because the output is pushing current over there and causing you to have pretty much, it's almost like you had 2 resistors coming from plus V dropped onto this 100K, and of course, that's going to give you more current and more voltage. So the voltage might be 6.2 volts whenever the output is fully at saturation, positive saturation. So what does that mean? Well, let's look at our input now. Well, our input is starting from 0 volts, and he's ramping up. Again, we have a triangle wave, ramping up. Well, he gets to the 6 volts. Nothing happens. Well, that's because the non-inverting input is being held slightly above 6 volts. Oh, see, that's the dotted line up there that's above the 6-volt line. We finally get to there, and the output shoots low. Well, now what's going to happen? The output is sitting at minus saturation of the op amp, and current is going to be sucked into the output through the 3 meg and lower the value of the voltage sitting here on the non-inverting input. So now we're going to start going low again with our triangle wave. Let's look at that. We're going low from that first one. We go through the 6 volts. Nothing happens because now the voltage is lower than 6 volts here on the non-inverting input. We finally get through that low threshold, and bam, it shoots high again. So what is the hysteresis protecting us from? Well, it's protecting us from noise on the non-inverting input or the input itself. And that noise can range within the plus and minus within the hysteresis zone on the signal at any time. Okay, as long as you're within the hysteresis zone, you're not going to be causing a lot of chatter, any chatter really, on the output of your comparator. So keep that in mind. If you're driving logic with your comparator, put some hysteresis on your comparator so that you don't get the chatter, you don't get the unexpected behavior in your logic circuitry. All right, going to the non-inverting comparator with hysteresis. It's now we have our output coming from the output of the op amp through the 3 meg back to the non-inverting input. And again, the ratio between this input resistor, in this case this 100K, and this 3 meg is going to determine how much hysteresis you have. The lower you make the input resistor value, the lower the hysteresis. The higher you make the feedback resistor's value, the lower the hysteresis. Okay, but the opposite is true. The higher you make the input resistor, the higher the hysteresis. The lower you make the feedback, the positive feedback resistor, the higher the hysteresis. If you make it too low, you can lock your op amp up, and your input will never be able to get your output to go out of saturation, whether it's negative or positive, whatever it happens to go into. So bear in mind, if you have a stuck comparator somewhere in something you're designing for one of your modules, and you've got it on the workbench, you're working with it, you might have too much hysteresis. That feedback resistor might be too low in value, or the input resistor may be too low in value. All right, I'm not going to go through the entire, exactly watching the waveform go up and down again, because it's very similar. This case, though, when it goes above the threshold that's being held, slightly high, well, no, let me stop myself. All right, this is working in a similar fashion, except we're not, all right, I'm going to stop myself completely. And I'll just start again here on this non-inverting comparator. Our input, when it gets above the threshold here and overcomes the current coming through the positive feedback resistor, that's when you will go high. And that is above the threshold voltage, you see. You have to go quite a bit above the threshold voltage, depending on the hysteresis, in order to get your output to go high. Then you've got to go quite a bit below that threshold voltage, that's 6 volts, again, in order to get your output to go low. And that's based on the feedback, that positive feedback resistor giving you the hysteresis. All right, let's move on. All right, pulse width modulation. This is a very popular sound for people to have in their synthesizers or in their noise boxes. Well, what's going on? How can I get it? How does it work? All right, well, we need an op amp. What we're doing on the positive input, or excuse me, the non-inverting input, that's where we're going to apply our signal. And again, we want a signal in this case that's going above and below 0 volts. So we're oscillating about ground. Okay, and here we show a triangle wave. Now, though, on our inverting input, we're not going to be going to a stable DC voltage. Instead, we're going to go to a modulated, low-frequency modulated triangle wave. We're going to feed that in through this PWM input, and now we're going to be changing the reference of the comparator on a constant basis. So let's say you were feeding in a 500 hertz waveform, that's this triangle waveform being fed into the non-inverting input, and you're feeding in about a 0.5 hertz low-frequency triangle wave to the pulse width modulation input. What you'll see on the output is that, first off, it's been changed into a square wave. So your triangle wave is now a square wave that's going between negative saturation and positive saturation. But the pulse width of it will be varying. So you'll be watching this pulse width kind of breathing, going back and forth. And when you listen to it, it sounds like more than one oscillator. And that's one of the cool things about pulse width modulation. So I invite you again, put these things on the breadboard, play with them, experiment with them. You will use them all the time in your synth DIY work. All right, let's take a look at the window comparator. This is whenever you have a scenario where you've got some voltage and it's going to be operating within a particular window. Say you want some module to do something if the voltage is within plus and minus 2 volts. But if it goes above 2 volts or underneath or less than 2 volts, like less than minus 2 volts, like the minus 3 volts or up to 3 volts, on the positive side, you want to do something. Well, that's where the window comparator comes in. What we've got is the input is being fed to the non-inverting input of the top op-amp and the inverting input of the bottom op-amp. Now, on the top op-amp, we have the inverting input coming from our bias network here. And let's just talk about the bias network real quickly. We got 10 volts on top, negative 10 volts on the bottom. We've got a total of 40K through here. And we've got a total of 20 volts essentially through this whole thing. So we are going to be dropping, let's see here, I think plus 5 volts and minus 5 volts across this 20K resistor. So on our top comparator, the only time the output is going to go high is if the input, that non-inverting input, goes above 5 volts. Now let's go down to the bottom comparator. Now his non-inverting input is seeing the minus 5 volts. Now the only time that his output is going to go high is when that inverting input goes below minus 5 volts. So now if we look over here to the little diagram showing this signal that's kind of going up and down and up and down and in and out of the window, we can see the representation of what the output of these two diodes dropped on this 100K resistor will be. As we're going up toward the bottom of the window, we're high, the output is high. We get into the window, that signal shoots low to ground here that's through this 100K resistor. And now we've gone up, we've traversed through, we've come out the top, and bam, we shoot high again, you see. And that continues as we go out of the window low or out of the window high. We are able to detect whether we're within that window or not. So that's the window comparator. Again, very useful in your modules and circuits that you'll be building in your synth DIY work. Alrighty, capacitors to the rescue. I've mentioned this before. Whenever you're using high gain, you may need to put a 10 to 100 picofarad capacitor across your feedback resistor if you're seeing high frequency oscillations out here on your output. Another use for small value capacitors in op-amp work is when you have a comparator and you want to speed up the output of the comparator. We have this small value capacitor fed back here, and what happens is when this comparator output starts to shoot high, you get a squirt of current through that little capacitor back to the input that makes it shoot high even faster, just as fast as it possibly can. So that's how you can really speed up your comparator output. Put a little capacitor there. This doesn't always work. In certain circumstances, it may cause more issues than it solves, but in a lot of others, this is a real handy thing to do. Okay, we're going to talk about an integrator very briefly. Okay, integrators. When you see a capacitor in the non-inverting feedback, the inverting feedback network of an op-amp, you're looking at an integrator. And what's happening here, it's just quite interesting. We've got our input resistor, and we've got this capacitor in the feedback network from the output back to the inverting input. Our non-inverting input is grounded. Well, if we put a voltage on the input here that is below ground and we start to suck current out of here, what's going to happen is the output is going to begin ramping up in order to push current through the capacitor back to the inverting input to satisfy keeping these two inputs at the same voltage, in this case at ground. Well, let's go to the right here. If we go above ground on the input and current starts to go in toward that inverting input, what's going to happen on the output is it's going to start to ramp down in order to pull current away from the inverting input here and keep this voltage the same as the non-inverting input's voltage of ground. So that's what's going on. The bigger the capacitor, the slower the ramp. The bigger the Rn, the slower the ramp. The smaller Rn and the smaller the capacitor, the faster the ramp. All right, now though, if we feed ground into the input, what will happen? The output of the op-amp will stand still wherever it is. So let's say we have been pulling some current out, like the situation on the left side top page, and it has started to ramp up. The output has started ramping up. And all of a sudden we put the input to ground. The output will stay just where it was, and it will just sit there, and the only thing that will affect it will be the input offset of the op-amp and the offset currents of the op-amp. Again, TL07 nice op-amp. It's got low offset voltages, low offset currents, and so that's like a ramp and hold scenario. You allow the output to ramp for a while, then you ground that input, and it will just stay wherever it ramps to. You can see some interesting applications there for kind of a sample and hold, a ramp and hold kind of module. Now, the thing with integrators is that if you don't stop the output from ramping up, let's say this current on the input keeps being pulled out, and the output keeps ramping up to try to provide current back through that capacitor in order to keep these outputs equal, it will eventually run into positive saturation. In the other case, when current is being fed in through Rin and the output is ramping down, it will eventually end up at negative saturation. So you have to have some way to reset the integrator. Now, in some oscillator circuits, you'll see that a JFET across that capacitor, which essentially shorts the output to the input, shorts the capacitor out, brings the output back to ground whenever the engineer or the designer wants that to happen. They turn that transistor on. But here's another way we can control it as we look at this bottom diagram. Here we see an oscillator. This is a little triangle and square wave oscillator, and it's using an integrator and a comparator. Well, what's going on? Let's take a look. We're going to assume that when we turn the power onto this thing, the output of our comparator, this TL07 here, pins 5, 6, and 7, is low, all right? Because whenever you turn on a comparator, it's going to be at VSAT plus or VSAT negative, one or the other. That's just what it's going to do. Trust me, it's designed to do that. That's what the circuit's going to do. So if we start low, now we notice that low voltage is being fed back through this 10K resistor. We got current flowing through there. We got current flowing through the rate adjust pot into the inverting input of our integrator, and it starts to ramp up, okay, because we're pulling current away. Well, what happens? When the voltage gets above the threshold of this comparator, its output is going to shoot high up to that little red line. Now, we're pushing current to the inverting input here. The output of our integrator is going to start ramping down until it gets, again, to the threshold to make our comparator go low again, in which case it does, and that cycle just continues to repeat. This is another circuit you could throw on your breadboard and learn a little bit more about integrators and comparators at the same time. To get more waveforms out of this little circuit, simply go across this 1 meg rate adjust with a diode. And depending on the direction of the diode, you will either have a ramp wave with a slow rise and a quick fall, or a sawtooth wave with a quick rise and a slow fall. Okay, well, that's integrators. Experiment with them. They're the coolest thing since sliced bread. All right, battery power. Let's just move on to this. I'm trying to go as quickly as I can here. I'm taking more time than I should. Battery power. You can power op amps with battery power very easily. They don't take a lot of current. And here are two ways. The way on the left, we're using a single 9-volt battery in order to get a plus and minus 4.5 volt supply with a virtual ground. And essentially, we're taking, and we have a voltage divider with these two 4.7K resistors across the battery. And then we also have these two 220 microfarad capacitors here as current reservoirs. If we need a dollop of current quickly, it can come straight out of there with low impedance, even when our battery begins to get older and its impedance starts to go up. So this is a good way to get plus and minus 4.5 volt supply for a pedal you're working on or something along those lines. Here we have two 9-volt batteries connected to give us plus and minus 9 volts. In this configuration, you can draw more current. You have the two batteries, and you can also have more headroom in whatever you're powering. Again, some pedals take two 9 volts. These days it's rare, but there you go. This is how you can provide battery power for your op-amp circuitry. All right, again, very brief look here at active low-pass, high-pass, and band-pass filters. Here we see the multiple feedback low-pass, high-pass, and band-pass designs. These are just a blast to play with. Put these on your breadboard, and just put whatever values you want in here and see what happens, essentially. It's that much fun. But, of course, it's a lot more interesting when you know what the frequency responses are going to be, the roll-offs are going to be, the cues are going to be, and so forth. So how do we do that? That's what we go to next. Online filter calculators you should know about. The Akawa electric design people have put a very cool filter analyzer and designer up here at this URL. The Texas Instruments Filter Pro program is totally cool. Go to the Texas Instruments site and download that and install it. I've installed it on my computer. It's fine. I'm a real virus, phobe, and it's totally clean. It was fine. And always virus check anything you're downloading. Let me just tell you that, okay? A little side note. Anyhow, thirdly, the Texas Instruments WebBench Filter Designer. This one I haven't played with as much, but it looks like a really cool tool for filter design. And I hope you get a chance to check these out. Well, I've enjoyed sharing this information with you. I'm happy to answer some questions now. And I hope that you're able to take something away from this and put it to work in your own analog synthesizer designs and work. So I guess I'll go ahead and ask Yasmina now. Let's go ahead to question and answer.
outstanding presentation, Ray. Thank you so much. Folks, we are going to take just a couple of questions as we are a little bit over the top of the hour. And let's start in just in the order they came in here. Lots of folks asking about polarized caps. So Nathan asks, why do you have a polarized cap on the input? What's the difference between a polarized and non-polarized practically?
Well, here, I'll answer that question. I actually have what's called a bipolar, and it's on the output. First, let me say this. Some people interpret capacitor markings that the straight line is a positive pole and the curved line is the negative pole. Some people draw non-polarized capacitors that way too. If you look around, you'll find that. Whenever I have a capacitor and I want it to be polarized, I put a plus by the straight side. If there's no plus, it's not polarized. So even though it may look like, you might have seen a symbol before that looked like that was a polarized capacitor. In this case, it's not. You don't have polarized capacitors on your inputs. And on the outputs, I'm using bipolar capacitors, which are also, they're the aluminum electrolytic technology, but they're not polarized.
Thank you. A few folks would like to know about LEDs. Can those be used in circuits for visual feedback?
Oh, absolutely. You can drive LEDs with the outputs of op amps. I would, as I say, reduce the current somewhat so that you get a faithful representation of whatever you're trying to amplify. But the output of an op amp can be used to give you a variable brightness in an LED very easily. And I would say just go ahead and put hook the cathode to your output of your op amp, the anode to the output of your op amp, the cathode to your current limiting resistor, which I suggest is at least 2K, and then experiment. And that LED should glow just fine as the voltage increases or decreases. Or, well, not when it decreases, but only when it's positive.
Great, thanks. Just a couple more questions here. Let's take a look. Mark would like to know, are only active filters able to resonate, or can passive ones as well?
Well, I think it depends on what you would be applying to the filter. You could get a passive filter to resonate, I'm sure. If you hit it with a real fast rising waveform, you will get some type of ringing. But it's far easier to use op amps because you don't have to have the large inductors that you would need to make really cool active filters. So that's why I just stick with op amps with active filters.
Great. And our final question we'll take is from Nathan. How does your integrator output differ from a comparator with the voltage set at peak? Well,
the integrator's output, it will eventually ramp up to V saturation, or it will ramp down to negative saturation of the op amp, but you try to keep it from doing that. Once the comparator has ramped up to V saturation, it's no different than the output of a comparator that is also sitting at V saturation, but the function of the two circuits is quite different.
Excellent. And with that, folks, we are going to say a very big thank you to Ray for presenting a really outstanding and informative webcast for us all today, and we thank you for sharing all your knowledge and expertise with us, Ray.
You're 100% welcome. Thank you very much. Thank you, everybody, for being here.
Folks that attended, we thank you for attending and hope you benefited from it. And we did have attendees from all over the world today, so we appreciate those of you who got up early and had to stay up late. So thank you so much. Lots of outstanding questions coming in from the group chat, Ray. Be happy to share that with you. Very exciting event here. Folks really enjoyed it. Folks, as we close out, we do want to let you know that we did push out a little code to you all in your group chat. So if you didn't open that group chat, please do open it. There's some information there to save you some money as a thank you for attending our event today. We have a special discount on Ray's book for you, again, as a thank you for attending the webcast today. We invite you to take advantage of that, and you can save some money on the ebook or print version, and lots of good information there to really help you with your day-to-day. Again, thank you, Ray. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.